in the background and laugh. Apparently that microphone is. Okay. It's alright. Is it still poor? Someone can give me a thumbs up or down. That will help. Oh, is this okay? Not loud enough. Okay. All right. Great. So the lapel mic is the way to go then. Thank you. So let's get started. Right. Thank you for the patience for working out the remote and online lecture stuff. I guess, yeah, we can appreciate the value of SKCDs, and a lot of them are actually quite relevant for machine learning. For this particular one, I would say, before we actually talk about machine learning, I would just like to caution everyone that machine learning as is, or the current setting, like basically the setting of supervised learning in particular, is about interpolation and extrapolation. And sometimes it can be wrong. So the two links I put down there, the video is from Michael Jordan, a professor in Berkeley. He's made many fundamental contributions across a diverse subfields of machine learning, especially graphical models. He has a well-known book and so on. So his take was machine learning. Oh, someone's mic is not muted. I'm hearing echo with people moving your mic. Yes, thank you. That's much better. That machine learning or supervised learning as it's practiced today is taking a giant data dump from yesterday, train your model, beat the optimizer to its best, and hope that it works for tomorrow. That doesn't mean that machine learning is not useful, but it's that's one of the salient limitations. So you can call this train test mismatch, or the challenge of distributional drift, and so on. The second link is linked to a book chapter that Professor Hao Dongmei, the third wrote in University of Maryland. I like his work very much, and he, in the this very accessible book chapter, he has this example of training speaker recognition modules using mainly male speakers, and they don't work from female speakers. Obviously, that's a big problem. For half of the world, they don't work. So let's get started with what we're actually going to talk about today. So we're going to get into some detail, or get into some of the nuts and bolts for those of you who hasn't taken IML, like your first machine learning model, so to speak, curve fitting. We'll talk about the model, the loss and error function, the concerns in overfitting, and how to do regularization. So these are quite crucial technical concepts that will reappear again and again in the next few weeks. This corresponds to chapter 1 of the book, part of chapter 1. And what I like about the book is that when things are important, they are echoed throughout. We'll get to see more of them. And then we will take a quick look at probabilities, the sum and product rule-based theorem. And we'll take a look at Gaussian distributions and how this helps doing curve fitting. So we'll see basically there are two different views of curve fitting that meet. And then we'll look at Gaussian distribution some more. So my personal feeling is that before I get into machine learning, I thought I know Gaussian distribution. But after I learned a lot more. So today we're going to have a geometric view of multidimensional Gaussian distributions. And next week, we're going to have an in-depth view of computing the conditional distributions of multivariate Gaussians, which turned out to be not so trivial. We'll briefly mention binomial distributions because you will be doing it in assignment 1. That is also to say that assignment 1 will be released early next week. And after this lecture, I think you can start taking a crack of it already. And I encourage you to do so. So again, the technical content from today, you're expected to see some probabilities and a review and brush up of derivatives and multivariate calculus. If it's been a while, finding station points and eigenvalues and eigenvectors. I also, my personal feeling is that I didn't really know what eigenvalues and eigenvectors were useful for after I learned it in first year algebra until I come across parts of machine learning, especially PCA. That was the first encounter for me. So in terms of coverage, I just wanted to briefly say today we will cover some of 1.1 and 1.2. We won't cover the rest of chapter 1, but they will come back throughout the class. We will cover Gaussian distribution, the top part. We'll mention the binary variables, and so the section of like the advanced material about Gaussians will be next Friday. So that's that. I'm basically the chapter 1 and 2 are very good. We're gonna keep coming back to it. Okay. So remember we said on Monday that machine learning is a computer program learning from experience E. In this toy example in the picture, the experience E are the 10 blue points. With respect to some class T, task T, in this case, try to fit or find a function form of this green line, which is basically a sinusoid function. And as measured by performance measure P, and hopefully improves. So this particular toy example is the sinusoid with noise will appear throughout, well, again, I would just like to re-emphasize the value of informative toy data, and this is what the book does very well in. I argue that being able to diagnose models against toy data is a crucial skill of machine learning engineers, and being able to come up with the best toy data for the task is a foundational skill if you want to do research in machine learning and design new models. So we haven't, right, you notice the gap. We skipped the performance measure P in this slide, then what is it, right? So before that, let's define some notations. We say we have n equals 10 data points. We have little x, in this case, one-dimensional, but we write it in a vector format, bold anyway, which is the input, target T is the output, and then x and t are both indexed by I. That goes from 1 to n. So because only the blue dot is what the learning algorithm sees. So we have to make a guess about what kind of function it is. And we will be essentially talking about this guessed function form throughout the first, actually 7 weeks throughout the kernel machines, because it is the good and bad guesses makes a difference, and there are many choices of making a very powerful guess. In this case, well, in the first lecture, we're just going to say polynomials is not a bad guess, because from calculus 101, we know that if we do Taylor expansion of any function at the point x equals to 0, it translates to polynomials. So we can, try to fit the function. Polynomials should be able to describe the function if we have essentially enough terms. So we basically have y of x parameterized by the parameter vector w. There's a constant term, and then there is a scalar multiplier in front of any other polynomials, and they are written in a summation form. So if equations like this gives you a pause, it's understandable. And we'll see actually a lot of, I mean, this will be a simpler version. Basically a simpler version of many notations we'll see for the rest of the class. This practice makes you more comfortable, I would say. So now let's talk about the performance measure P we skipped, right? The performance measure is, in this case, we take it as basically square errors. If you have taken statistics or actually in linear algebra, we know that square errors are a good idea for measuring performance of many things, including this case. So the figure 1.3 actually visualizes the square error by saying if our current fit of function y is this red curve, then the square error is basically square of the length of these green stems, the distance between the blue dot and the red curve at the same x value, right? So we wanted to minimize the square error. So what we have not addressed is what should, how many of these W terms are, right? So we can imagine for now that there is an algorithm that finds the optimal set of W's given the number of W's that we want. Right? We'll cover several versions of such an algorithm in a little bit. But basically, if we only have the bias term, we can fit a flat line. If we have a bias and a linear term, as in the right-hand side, we can fit a straight line. And if we have cubic terms, we can fit something as wiggly as a sinusoid, but not quite. If we can have, it turns out that one can actually have too many terms. If we fit a nice ordered polynomial here, the line is too wiggly and it seems to be fitting the noise. And towards the edge of the graph, you can see that the fit actually has large errors, right? So this is a good time to talk about the concept of training and test and how to measure errors. Especially for those of you who haven't, this is the first machine learning course. So for example, for the ninth dimensional polynomial, we can see that the line passes through each blue point perfectly. So in the square error terms mentioned 2 slides ago, the square error is actually 0 in this case, meaning that it fits the training points perfectly, and we cannot find a better fit because the error is already 0. But in machine learning, we just like in real learning, you learn some material and then you see the test. In this case, the test for the algorithm are 100 new points, right? So we train on 10 points and then we give it 100 new points generated from the same toy function that we specified at the beginning. And then in the bottom, figure 1.5 contains a graph of the root mean square error computed on the training and test set respectively. Right, and then we plot essentially the root mean square error called E of RMS for both the training and test in the graphic below. It's divided by n, whereas in 2 slides ago it wasn't, because it makes the error comparable. Otherwise, the error on the test set or on 100 points is going to be just dominant in magnitude. So it's normalized by n. And then we can see that training error is in general lower the x-axis is m, the order of the polynomial. There is a sweet region or sweet spot basically here. The test error is the lowest, and as we can see, when m is 9, or in this case being too large, the training error goes to 0, but the test error shoots up a lot. So you might ask, why is this the case? Since this is a polynomial curve fit, we can actually examine the coefficients being learned, right? So if we just fit a flat line, it's 0.19. It's not bad because the function was sine 2 pi x plus noise, right? So we expect the mean of this is around 0. And then if it's 1, m equals 1, we get some terms for both the linear and constant term. I think there is a typo in this case. This should be m equals 3 in the book, right? And something strange happened when m equals 9. We can see that all of these coefficients here, even including the linear term, is really huge. And that does not look right, right? We know that Taylor expansion, higher order polynomials tend to vanish, but in this case, they not only don't vanish, but also to dominate the terms. What happens is that because we're fitting polynomials, going back to the last slide that has a picture, when the value of x is large, the polynomials are going to become either really big on the positive side or really small or large magnitude on the negative side, as we're seeing here. So here and here. In other words, polynomials are unbounded. Back to the starting comic, the problem of machine learning for extrapolation with basis functions such as polynomial is that outside of the range that we observe, they become unbounded, and that can be a problem. So we have an apparent problem here, and this is called overfitting. Okay, and so how do we solve this to an extent, right? So the first cure we can come up with was, hey, our test data is 100 points. Why don't we assume we have both of the collections? Why don't we use more of the data points for learning? Indeed, as figure 1.6 shows, having more data points improves visually the quality of the fit, right? If we have 15 points, the line still tracks the, it starts to track the training or the target curve better, and it's less wiggly, so to speak. If we have 100 points, the fit is actually pretty good, right? So increasing the data points reduces the overfitting problem. Cure number 2 is called regularization. So if the perceived problem is that, let's say, W9 and W8, so they becomes really big, right? That's the problem. We can say, let's try to fit the same error function, and we want the W's to be small because that's intuitively better. And this is called the regularizer term. In this case, if we want to penalize large W's, we just put the 2 norm of the W vector as a penalizer term. This is called the L2 regularization. So we'll see more of this again and again. And for those of you who have played with neural nets, this is, yes, a common regularizer tool that's actually in use. So let's do this. Notice there is, like, we just added something in order to solve a problem, but there is no essentially free solution. So the price to pay is now we have this additional lambda parameter that nobody really are telling us what it should be. Like, what's the appropriate weighting between the error term and the regularization term is unspecified, so to speak. Well, this is called hyperparameter. But let's say just try a couple of different lambdas and see how it works, right? So if we put log of lambda equal to 0, meaning lambda is 1, then we're essentially weighing the norm of the weight and the error term equally. That seemed to be regularizing too much in that most of the large subsequent W's goes to 0 and the resulting red line looks like a straight line. So then we say that, well, let's decrease lambda, right? If natural log of lambda is minus 18, that means lambda is a pretty small number. Okay, my slide was just gone. Okay. What happened? Apologies, my iPad went to sleep and then it stopped my screen share. Let me start it back again. There we go. Right, so if log of lambda is minus 18, because it's hard to essentially pronounce or read a really small lambda, it's better to look at them, talk about them in log terms, meaning lambda is pretty close to 0, then the curve looks like more like a sine curve, right? And these are ninth order polynomials, meaning that there are still 10 coefficients, but the curve seems better behaved in this case. In fact, if we examine the coefficients again, so if log of lambda is minus infinity, meaning lambda is 0, no regularization, that was the table of coefficients we saw. And then if you look at these, the case of these two regularizers, we can see that we still get, for lambda equals 0, the coefficients vanish almost too quickly. Basically, this first, second, and third order term are already pretty close to 0. If we do log of lambda equals minus 18, then there are still significant amount of volume in the higher coefficients, but they don't make much of a difference. This is also this also seems to be influenced by our value of x, meaning in the training data set, the x is between 0 and 1. Meaning if we take the larger order polynomial, exponentiate x is only going to get smaller. But if instead we train on 2 cycles of the sinusoid, then large coefficients of the higher order polynomial would not be good. I'm hearing, okay, great, echo is gone. So here's another learning curve. So these basically errors or objective function against some parameter are generally called learning curves. They are very useful, not just in as a conceptual value, but they are super useful in practice. If you're doing any machine learning, you should, yes, design and generate your learning curves as one of the first tasks. So in this learning curve is different than the one we saw a few pages ago, right? In there, we had a few pages ago, we had error against polynomial order n. Here we have error against log of lambda. We kind of see the same effect. Essentially, the test error has a sweet spot or 3 region in the range of lambda, in that there is no one good lambda, but a range of good lambdas. And right, the larger the lambda is, the higher the training error here, because lambda modulates the regularization term, and we're essentially trading off regularization against training error. So the training error don't go to 0 in this case. Yeah, and the test error goes up if we regularize too much or too little. So in both of these regions, we have higher test error. Another read we can get out of this is that learning curves are essentially multidimensional objects, right? We can envision having basically the error, training and test error against both polynomial order m and log of lambda. These are both hyperparameters of the learning algorithm. And we should essentially pay attention to which dimension we examine, or whether we examine them jointly. Another thing I like about this book is that three-dimensional plots are inherently hard to interpret and analyze. Simplifying things down to two-dimensional plots are good in general. So here's what we did. Basically, section 1.1 of the book. We looked at polynomial curve fitting. We defined at least one loss function, at least one regularization term, and we looked at the phenomena of overfitting and how to overcome it. Are there any questions so far? Okay, that's simple enough. If we're happy, we're going to move on and examine probabilities.
Sorry, could I ask a question?
Sure.
Right. So when we were looking at the cures, it is the solutions to using higher order polynomials, but not rather decreasing. So if we have to use a higher order polynomial, we can improve the results by adding more data or regularization. Is that it?
That's a good question. Let me try and answer it from just this lecture, and we will see more of it later, like especially in neural networks. In here, we're using the term higher order polynomial as a general substitute for more expressive models, right? So we can, or more flexible models. I hope that makes sense. Meaning, so the notion of overfitting is that if our model is too flexible, then it will fit the noise. And the symptom of that is that training error is very low, but test error is very high. And yes, the two ways that we saw so far to overcome it is that we get more data or we regularize. So as we will see in the next week or so, basically, or actually in your assignment as well, regularization can be seen, interpreted as a form of prior, basically what we believe the model should look like. And there is actually a mathematical trade-off between how strong our prior belief is and how much data we see, which is very interesting. You will, your assignment 1 derivation part will tell you about that in coin toss terms. So let me say that, yes, these are the ideas, then they are somewhat inherently connected. And I hope that that's helpful.
Thank you.
Sure. Okay. Right, so let's move on. So I hope this will be familiar to the vast majority of you. If not, brush up on probabilities, and there are many great tutorials on the web, such as Khan Academy. There might be a few links in the course homepage as well. So let's just refresh our memory about probabilities. Let's start from the discrete probability. So if we have two variables, x and y, in this case, we think of them as a grid, where y has 3 distinct values and x has 5 distinct values, right? In this particular case, we have the joint probability P of x, y, the big X and big of y. If we sum over basically x goes from 1 to 5, y goes from 1 to 3, they should normalize to 1. And in here, we're also inherently assuming that, let's say we have n samples. And so p of small x I and then y xj is essentially, well, the estimate of that, or maximum likelihood estimate of that, is basically the counts in each cell nij divided by big N. Right. The sum rule says basically for a joint distribution, we can marginalize or derive the probability of one of the variables by summing over the other variables. And in this picture, P of x is represented by Ci over n, basically the column sum over all the samples. And it is also sum over the cell counts over j from 1 to 3 over n. Right. So this is what the sum rule means if we have essentially a table of counts. It's also good to remind ourselves of the product rule. So the product rule says that the joint probability is the product of the margin of one variable and then the conditional of the other variable conditioned on this. So if we materialize this in this probability table, we will say that probability of little yj given little xi is, according to this equation 1.11, we do p of xi yj divided by p of x xi, right? And from what we already wrote, that is p of x is sum over nij that goes from j from 1 to 3, and the p of the joint is nij, and the big N cancels out. So if we have a probability table, in other words, the conditional distribution is simply the value of the cell divided by either the column sum or the row sum. All right. So Bayes' theorem basically is an extension of, well, can be easily derived from the product rule, right? So written as is, it basically flips the conditional. When I say flip, is we're essentially computing the p of, say, y condition on x from the p of x given y, and that scaled by the ratio of the two priors. So it's very much simple looking, this equation 1.12. But it has so many non-trivial applications throughout this class and in general in the field of machine learning, which I hope we will appreciate over time. So also on this page, there is another picture of the probabilities x and y. So another way of representing, let's say, the marginal distributions, that is somewhat similar to continuous distributions, which I won't get into for this lecture. I encourage you to look it up, is the histogram, right? So in the last slide, we basically says, hey, the marginal distribution are these, we call them CIs, right? But we can visually graph them, and they are very intuitive to look at. So in this particular picture, the point is in a lot of cases, our discretized data actually has an underlying continuous measurement behind it. How to discretize is another question that we won't touch upon in this class, but is worth to be aware of. So suppose we discretize y in 2 buckets or 2 bins, and x in this case in 8 bins, I believe, or 9. 9 actually, I miscounted. Okay, and the margin distribution of y are 2 bars that like are equal, almost equal in length, and then the margin of x is like a set of 9 bars that are higher in the middle. So an interesting thing happened if we essentially conditioned p of x on y equals 1. So that corresponds to this row in this picture, meaning visually we see there is more dots, blue dots onto the left, and we also see this in the conditional distribution that is computed here. So it's right. Let's say we can, yeah, we could use Bayes' theorem to compute p of y given x as well, but this serves to say that the mental picture or the visualization of conditional distributions can be quite different from marginals, and we'll see this again next week in continuous variables. So I won't go through how we go from discrete to continuous variables, which essentially include taking the limit of these histograms with the bin size going to shrinking to 0. But a lot of you would know that so we can have joint distributions in 2 dimensions as well. Let's say call it small p and p of x and y. In order to visualize this, we will have to envision sort of a 2-dimensional heat map or a 3-dimensional where x and y are the axes and there is a height dimension signaling the probability density, right? So the sum and product rule works exactly the same way. For well-behaved classes of p, x, comma, y, let's not get into what well-behaved means. Let's for now assume that the vast majority of distributions we're working with are well-behaved. So if we integrate y out, we get marginal distribution of x. And at each given point, again, well-behaved in here means that we assume that, for example, p of x and p of y are not 0 elsewhere. Otherwise, Bayes' rule would not work. We can't divide by 0. Like the joint probability is the product of the conditional and the marginal probability. There is also this quantity called the CDF, cumulative distribution, which is the integral of the density function p of x. It basically is a curve that goes from 0, 0 to 1 when x reaches the right-hand end of its domain, either infinity or the maximum value if x is bounded. So here is just another view of Bayes' theorem that is written in machine learning nomenclature or notation, so to speak. Therefore, I think it's worth looking at it again. So the vector W, we can think of it as weights, starting next lecture, or parameters of your model. And then the curly D is data. Actually, a data set, one particular set of data. So in here, we're essentially saying we would like to estimate on the left-hand side. This is posterior of the model or of the model parameters that we'd like to estimate. So think the weights of the polynomial curve fit in the first half an hour of today. Given the data set we observe, or the 10 blue points, is equal to probability of the data given the weights times the prior of the weight over the prior of the data, right? So this interpretation is useful in different ways. So more often the posterior is hard to essentially just write out directly. But very often, if our model is well specified, basically remember y of x given w, right, was the function we looked at. This is well specified. Then the likelihood, this is easy to write and evaluate. And then the prior, because it represents our belief, it should be also well defined. And you may wonder, right, what happened to the denominator, right? Why did that disappear? So where did that go? The answer is for most of our class, basically the first machine learning class, we're going to assume that the data set are given and we are working with one data set. So we're not comparing different data sets within this prior and likelihood framework. So given the data set, the probability of this data set exists is actually constant for different values of parameter W. Therefore, yeah, it's omitted from the expression below. So we can leave it at that. And next Friday, we're going to see a concrete example of this. So let's review a number of key quantities, right, of probability distributions. And here let's say we assume the random variable is x. Okay, where's my pen? So this is the random variable. And it's then PDF is p of x. So expectation of a function of x over its distribution is e of x is written basically like a weighted sum of f weighted by the probability density. So one tricky point I would like to point out is more often than not, as in this case, we write the notation of expectation of something, but what the expectation is taken over is often omitted. And that's sometimes it's tricky. A lot of times it's obvious, but a lot of times it's not obvious and it's not necessarily written out, especially for an audience who is new to machine learning. This can be a roadblock in making sense of some of the expressions. So I'm going to write it out for this particular one. There is only one variable x, so the expectation is for sure taken over x. And here, so as you can see, it's actually written out in 1.41, right? So the variance is basically the deviation of f of x with respect to the mean value of f of x, right? And it expands to basically the difference of the expectation, again, over x for f of x squared and the square of expectations. So you would have known all of that. And the covariance of two random variables, this is where things get interesting, is basically expectation of the product of their respective deviations from the mean, where the expectation is taken over the joint distribution of x and y. So the underlying assumption is there is a p of x and y, and you can write out the integral form as well. So the last one, the conditional expectation, is a little tricky. Let's say, right, this can have two variants in here. In the most general form, so we're still taking an expectation of the function f with respect to random variable x, but conditioned on random variable y, right? So therefore, if we assume x to be discrete, it's easier to write in here. Compared to the equation at the top, we are replacing p of x with p of x given y. And that seems on surface simple. And the outcome of this is, instead of being a number, which we would expect, say for the expectation of f, in here we get a function of y. Basically, the expectation of f in here depends on the value y, what value y takes, right? Okay, so I hope this is all familiar. Again, so I feel it's helpful to think about which when you see expression like this, which symbol is the random variable, which thing is being marginalized over, and then what the output is, whether it's a number, whether it's a function of something, and what that something is. I won't answer on the spot, but people can think about whether the expectation and variance of a random variable without conditioning always exist for different kinds of distributions. So the spoiler is, if you have heard of the dynamics of large networks or have taken my class on network science, there are some interesting answers there. We can discuss on Piazza on this if you like. So let's move on to Gaussian distributions in one dimensions. Again, this is mostly a review. I assume you would have all seen the Gaussian distribution. And it looks like a bell curve. The mean is where the middle of the bell curve sits, and sigma is standard deviation or square root of variance. And it's basically the width under which, or 2 sigma around the center, is where about 68% of the probability mass sits. So one can generalize this expression, and there's a normalizer term in front, right? So the crucial thing to note is this is the quadratic form of x parameterized by mu and sigma, and this is just normalizer. And same thing goes with multidimensional Gaussians, which we will delve into in some detail. Again, this is the normalizer, and then the quadratic form written out in matrix and vector form. Basically, right, so x minus mu transpose is this long and fat vector multiplied by the inverse of the covariance matrix, which is square, and then multiplied by x minus mu, which is the actual vector that's a column vector. So the product of these turns into a number, right? All right. So one of the very useful heuristics is maximum likelihood. So we talked about likelihood sort of loosely a few slides ago when we talk about Bayes' theorem. So here's an actual example of what a likelihood is. So a likelihood is essentially the probability of observing a bunch of data points, not just one x, but a bunch of x, given a model. In here, the model is simply the Gaussian distribution. So the bunch of x's we have here are the black dots, and the value, the likelihood of each point is essentially the height of the Gaussian probability, right? And the likelihood for this particular data set D, right? This will be clearly D at the point at this moment, is because these points are drawn IID from the same Gaussian, the probability of the data set is the product of individual probabilities, right? So remember from the last slide, this normal distribution term is essentially the constant, the normalizer, times the quadratic form, the exponentiated. So it's handy to take the log of that. So if we do so, we get back this, which is the quadratic form. And then the log, right, the log of the normalizers too. Because there are n data points, the normalizer don't change with respect to the data point. Therefore, there is the multiplier n in front. So the task is, if you have taken stats, this is again a reminder, we observe a bunch of these black dots, and we would like to know what mu and sigma is, right? Essentially here we write out the likelihood, assume there's some value of mu and sigma. Now we want to find the values of mu and sigma that maximizes the likelihood, right? So we want to maximize the log likelihood. Log is a monotonic function, therefore maximizing the log likelihood is equivalent to maximizing the likelihood, right? So this is where our calculus comes in, right? If we differentiate the log likelihood, like I call it this L as a function of mu and sigma, or sigma squared, equals this, right? So we differentiate L with respect to mu. We can immediately see that we don't need to care about the last two terms. We get, well, there's a square term, and then there's 1/2 that cancels out. So 1 over sigma squares. So we differentiate with respect to mu. Sigma we look at it as treated as constant. And then the summation sign stays as the same. It goes from 1 to big N, xm minus mu, right? So is there something wrong? So the chain rule says, right? So this is a quadratic term of mu, but then we also need to differentiate the inside of the quadratic term with respect to mu. Therefore, it is we should flip the sign because the sign of mu here is negative. So that's what we get, right? And we want to maximize this. Therefore, it's a stationary point at which the derivative is 0. If we set this to 0, we can ignore the sigma square here. What we get is essentially sum of xn, little n goes from 1 to big N, equals big N times mu, right? And if we just move the n to the other side, we get the intuitive answer that a lot of you already know. Basically, the maximum likelihood estimate of mu is the average of the data points, right? So we can do this similarly for sigma. In this particular case, we can plug in the maximum likelihood solution of mu in there and then solve for sigma. That might be easier, right? And what we get is sigma of ML is also 1/n, essentially x and the difference between x and mu squared, sum from n goes to 1 to big N. So for those of you who have taken stats, you would know that this is not the solution or recipe you get in statistics, because this solution is what's called biased estimate. Despite its maximum likelihood, what that means is if we take the expectation over different data sets of different sizes, it does not converge to the true parameter sigma squared. Right. So one way to intuitively understand this is that if we have one single data point, maximum likelihood will give us an estimate of sigma that's not, well, that's zero essentially. If we have one data point, the mu is that data point, and then the sigma squared is zero. But in reality, it is not, right? It should be, if we have one data point, the variance estimate is not really defined. We can't look at the deviation of something with respect to itself, right? Also, well, one criticism to this term being unbiased, as we will see in next Monday, is that the word biased carries a negative connotation. Unbiased estimator is not necessarily better in a lot of cases, and there's a trade-off between bias and variance, as we will see. So basically, in order for the estimate to be to be unbiased, we add this correction factor 1 over n minus 1. Right. So here's also a picture of how bias could arise using maximum likelihood. Right. So the green curve is the generating distribution. In fact, this I believe this picture is updated. There's an errata on this. So basically, there are two blue dots in each of these estimates. If we do maximum likelihood estimation, we get the red distribution. As we can see, they are not they're quite far from the green distribution. And both the mean and variance estimate, the variance is being underestimated, as we said. The mean accurate estimate is also not great. So I would say this is an illustration of what both how bias can arise and how variance can arise. Back to our point about more data. If we draw more data points from the green distribution, then it's going to be unlikely that multiple of these data points lie on one side of the green distribution, right? So the question, food for thought for this particular part is, does high bias and variance means that the model is overfitted or vice versa? It's a trick question. The answer is actually no. The overfitting is diagnosed by essentially the expressivity of the model class we chose, and we can observe it by contrasting test and training error. But bias and variance here simply means how close the model parameters are to the true estimates and how that varies across different data sets. I hope that makes sense. So I see there are some questions. So we can pause and answer them. Let's say we're at an hour. Let's see, we have a bit more to go, but let's answer some questions. Ella's question. So is P of X practically zero? I would say no. It's quite a deep question. I don't think I have the right answer. again, I don't feel I have the right answer in full depth on the spot, but in a nutshell, this is what I think. So here's a toy example to help us think about this problem. So if we have p of x, let me go back to that slide. Oh, here. So if p of, let's say if we have p of d, that has, yes, let's say x drawn from Gaussians. But our prior says that we can only have two valid Gaussians. One look like this, one look like this, right? Then the probability of any particular data set is conditioned on either model, and it's not zero. So I hope we can live with this answer, at least for the lecture, for the time being, because, right, so how to compute p of x is yeah, it's a tricky question. Right, it's tricky because we might need to then consider normalizing against different models, and computing normalizers is not always an easy task. Okay. And Rachel Barker provided answer to that, I suppose. I wouldn't try and read it on the spot. Let me try and read and answer the next question by Noah Hinton. One jargon explanation I heard was that 1 degree of freedom out of n is used up in the mean estimate, so that variance gets n-1. Yes, that is true. That is yes, I agree with that interpretation. Just bear in mind that, right, that interpretation leads to the unbiased estimate, doesn't lead to the maximum likelihood estimate. So one can argue that the maximum likelihood estimate is quote-unquote incorrect for Gaussians, which is, yeah, which I think people can subscribe to. But as we will see next Monday, I guess, whether being unbiased is incorrect is actually, I would say, a historical jargonary sort of, no, it's just a term. Right? Or in other words, I feel considering the trade-off between bias and variance allows us to have sort of a richer set of languages to discuss parameter estimates than like in statistics 101 as I have taken it. Yeah, good question, thanks. So let's move on. So why are we talking about Gaussians and curve fitting? So here's why. We can basically have a probabilistic view of what curve fitting does, right? So think of this red curve as what we were trying to fit the sinusoid function at the beginning. And one intuitive way to express our model is to say that we have some parametric form. Okay. So in machine learning, also the word model is quite overloaded. In this class, we're going to use this as basically the functional class that we are trying to learn is the model, right? Sometimes the model refers to the result of the learning. Basically, let's say your coefficients saved in the IPython file, and that can be called a model file, right? Or an array. So in here, if we call yx given comma w the model, then the probability distribution of the target t given data weights and additional parameter beta, which encodes the inherent uncertainty of the observation given the model. Then the picture goes like this, right? So if the true curve is the red one, what we can estimate, even to the best of our abilities, is this blue little bump, right? Because observation noise is inevitable in many physical processes. For those of you who have done a physics lab, you will know. For those who have not, you can also understand that our readings of measurements is not necessarily perfect, right? So in a continuous world, we can't avoid having this little bump of uncertainty parameterized by beta. In here, you might notice slightly different convention. We're used to seeing variances in normal distributions, but here we're looking at beta. It's called a precision. That's the terminology. And it's the inverse of the variance. So right now, we simply just inverted the variance and call it something else, or in here, it might be inverse of the variance squared. But in multivariate Gaussian, looking at precision will be more convenient than looking at the covariance or covariance matrix directly. So we'll see more of that next week. So basically, the mental picture is for every value on this red curve, we have this inherent blue bump of uncertainty, blue little bell curve. And we could try and infer not just W, but also the observation noise beta from the data, which is attractive. And it gives sort of us a richer language to think about curve fitting and discuss it, right? So here is what we do. Let's say we've worked with W's for a fair bit. Let's now try and work with the beta in the way we did 10 minutes ago with the Gaussian distribution. So I just copied the equation from the last page, 1.60. And now we have multiple estimates of x and t. So these are vectors. So it's also helpful to get used to these conventions. So if they're handwritten, I will usually try and do like a vector sign on top. Right, but in the book, vectors are bold, scalars are not bold. So if we have multiples of x and t, and scalars have subscripts, right? We basically multiply we assume the observation noise is independent of each other, so we just multiply the probabilities together. We take the log again, same deal with the Gaussian probabilities. And now we have essentially the first term, the quadratic term, that has a beta in front. In here, notice that with sigma square, we would have like minus 2 sigma squared, whether it's squared, right? Just checking. Yes, it's minus 2 sigma squared. And with beta, the beta is on top because they are just inverses of each other. And then sigma square or beta also appears in the normalizer term. Therefore, it's here. It's in the second term as well. So assume, again, magically we have the maximum likelihood of estimate of W. We know of a good W, let's say phi bar or polynomial curve fit. Now what's our value of beta? Again, we differentiate against 1.62 with respect to beta. We can try and do that on the spot. Let's say log of this log of p term with respect to beta. The last term is not very relevant to beta. The second last term is basically n over 2, and then log of beta differentiating that is 1 over beta. And then the first term goes like, oh, this beta is actually a linear term with respect to beta. So we essentially have minus 1 over 2 and the same sum, right? And goes to 1 to big N, and then y of x and w minus t of n squared, and plus that. So if this whole thing is 0, right, there are different opposite signs, so we just move the whole summation sign to the other side. So 1 over beta, which is then also sigma squared, is essentially 1 over n, and deviation between the predictor or what the model predicts the function is against the observations. So this is basically our maximum likelihood of sigma square again, right? Which is again not unbiased. And here is another thing that having a probabilistic language over curve fitting allows us to do, right? This is what's called predictive distribution. I feel this is talked about less often than is good for the community, because right now, more often, if you run a deep neural network, you will say cat or dog or 0.95 cat, but it does not give you essentially the cloud of uncertainty about that 0.95, right? Is the model really unsure where it could be random guessing, but it also could be 0.95, or is it just it's almost sure that it's 0.95? So the predictive distribution intuitively visualized can be as follows. Basically, if we have the red curve, then at any point, basically this is the function of y. Okay. So this is the function of y of x comma w, right? Then at any point, we not only predict the most likely y or the mean of the function form. We will see that the best predictor given this blue bump of uncertainty is the mean of this Gaussian. Should be intuitive. We can also plot the variance, or say 95% confidence interval of this prediction, which gives us this pink cloud of uncertainty, which is very useful. We'll see this again next Friday. So what we did so far is, well, one-dimensional Gaussians and probability tables and probability quantities and how they apply to curve fitting. Okay, we have 15 more minutes. Let me try. So because today there's no lab, I won't try and end at an hour. So let's look at Gaussians in 2 dimensions. I feel this is sort of an underappreciated topic in probability and stats, and for some of you, it might be obvious already. I'm also confident that it's not obvious to everyone yet. I can also tell you that the 2-dimensional Gaussian or multidimensional Gaussian intuition is what I use to interview PhD candidates in my lab, and not everyone gets it. So here is Gaussians again. We just saw this picture a few slides ago. It's worth talking about why it is cool, roughly. It will come up like on and again. So the first reason that it's cool is because of the central limit theorem. For a sum of a set of random variables, which of course itself is a random variable, so the distribution of that becomes increasingly Gaussian as the number of items in the sum increases or goes to infinity, roughly speaking. So the bottom figure is an illustration of that. Basically, if we have random variables that are uniformly distributed, and as we will see in, even if we have a coin toss, so if we sum over these sufficiently large number of times, let's say if we sum over 10 uniformly distributed random variables, it already looks like Gaussian. And the upper right-hand picture plots coin tosses. Basically, in here, we just have 2 probability bars. And then over many coin tosses, the distribution is still discrete, but it sort of, if we look far away, it looks like Gaussian, right? So that's central limit theorem informally. And another cool thing is the maximum entropy result. So we have not covered what entropy is yet. Some of you may know from physics. It means a different thing. Some of you may know if you have read about or taken the information theory class. It means basically a way to quantify the uncertainty for random variables. So if we're doing a coin toss, informally, the maximum entropy state is when the coin is fair. Basically, before we toss it, we cannot guess what the outcome is, right? So it turns out that for continuous distributions, Gaussian is the maximum entropy distribution that we can get for a given variance. Well, mean doesn't matter for measures of entropy, but for variance does. So that's kind of cool. We will also see this again in when we look at priors and Bayesian estimates of distributions. So for Gaussians, it's also its own conjugate if we look to estimate the mean, which is again cool in a computational and I guess mathematical way. So let's just stare at the multivariate Gaussian equation a bit more. And the goal of this section is to give us more intuition of this thingy, or so-called covariance matrix, that appears twice in the distribution. As we said, the first one is just a normalizer, but let's just say we have random variables x1 and x2 as drawn down here, right? And the covariance matrix is a 2x2 matrix. So we call basically sigma 1 as the variance of x1, sigma 2 as the variance of, or standard deviations, or sigma 2 squared as the variance of x2. And then the covariance matrix is a symmetric matrix. I forgot if there's a square there, but I'll just write it. Actually, there isn't a square, so my apologies. It can be negative, right? So let's just denote it as that. Just messed up again. Okay, there we go. So what does this matrix mean? Okay, my iPad has locked me out again. Let me reshare the screen. Yep, should be up. Right, so what does this little 2x2 mean, and what does it mean for the for the expression of two-dimensional Gaussians? As we know, in one dimension, sigma squares is roughly the width of the bump, right? So, So the simplest case of a two-dimensional Gaussian is where x1 and x2 is actually, they distribute exactly the same, and there's no correlation between the two. And I hope you already know what correlation means intuitively. If not, ask the tutor or go brush up with Khan Academy. So basically in here, intuitively speaking, if we take any slice of horizontally and vertically, the shape of the distribution don't change, right? So roughly, let's say, we can intuitively think of sigma in here as the width of this two Gaussian bumps. Now, it's also useful to get mentally used to contour plots, right? These are, as we said, two-dimensional distributions are essentially three-dimensional plots. We should think of them as a probability mountain with a bump in the middle. And the contour is basically equal height lines on the mountain for what is called here isotropic Gaussian. The contour plot is circle, right? So if we move on to the plot B in the middle, it's sort of an ellipse, but with its two axes, major and minor axes, parallel to the x1 and x2 axes. What this means is that like we can basically look at this contour plot and then mentally ask ourselves what the marginal distribution is. In here, the two marginals are Gaussians, but their width is different, right? In here, sigma 1 squared is greater than sigma 2 squared, like it's for fat ellipses. And then the correlation is still 0 because they are axes parallel. And if we take basically P of x1 conditioned on, let's x2 equals 0.5 is the same as P of x1 of x2 conditioned on x2, say some other value, 0.2, something like that. Or in general, P of x1, x2 is the product of the two marginals. So we can actually verify that in the expression above, 2.43, because when a matrix is diagonal, its inverse is simply the inverse of its diagonal elements, and we can decompose this quadratic term as basically two separate quadratic terms about x1 and x2. Right, so in the most general case, it's a rotated ellipses. So, right, so we can kind of say, oh, the major and minor axes of the ellipse is slanted. And the rotation has something to do with this cross term sigma 1, 2. Intuitively, in this particular picture, x1 and x2 are positively correlated, or sigma 1, 2 is greater than 0. If the ellipse is slant the other way, then sigma 1, 2 is less than 0. It's negative, right? So that's in a nutshell. I think I saw some comments coming, but they're not in the channel chat. I wonder, yeah, this is, are they in meeting notes? No. Okay, there were some questions about x1 and x2. Right, so if we don't get to, if the next slide or so don't address it, you can ask me as a question. Let me see, we may not have time to go through all of this, it looks like. So I'm going to give the high-level version of this, and if needed, we can maybe spend next Friday going through some of this. So the next few slides basically is my way of saying this is a good place to brush up on eigenvalues and eigenvectors if you haven't. So I'm going to stick to the geometric interpretation in slide 31 here. So as we were looking at the slanted ellipse before, and said that the major and minor axes are this way, but what it means is the length of the major and minor axes are essentially square root of the lambdas, or the eigenvalues of the covariance matrix. And then the direction that they are pointed at, right? So this is the rotation matrix, the U1 and U2 here are the rotation, or they are the eigenvectors of the covariance matrix, which I think is fairly cool, right? Where take a piece of linear algebra and then we can see it visualized in 2 dimensions, in the Gaussians. This intuition also holds for higher dimensional Gaussians, except we can't draw them as easily. There's another cool insight about this term in front. Basically, the square root, 1 over square root of the determinant of sigma is, so the determinant of the covariance matrix is intuitively the volume of like a high dimensional, the covariance. We can see that by thinking basically the determinant or sigma, like determinant of the sigma, once we have diagonalized the sigma matrix, is essentially product of these lambda i's. I goes from 1 to the dimensional, right? Meaning it's the product for the 2 dimensions, it's the product of the long and short axis of the ellipses. So that's rather cool. Let's see. I do want to say one word about binomials, so that those of you who want to, and I encourage to start taking a crack at the conjugate prior assignment. So if we look at coin tosses, right? So assume the outcome of coin toss is denoted as x, and it takes between 2 values, 0 and 1. The Bernoulli coin distribution describes the outcome of the probability of one coin toss, basically the with biased coin mu, right? So the probability is mu when it comes up heads or 1. The probability is 1 minus mu if it comes up 0. And binomial distribution is simply like the probability of n coin tosses. In the sense that we basically, there's an m choose n term. Basically, m of these coin tosses come up heads, and then the rest come up tails. So we already saw this picture. In assignment 1, you will show that the prior distribution for a coin toss is the beta distribution. It might be scary looking, but these are normalization terms that you have some guidance in working through. What's cool about this is that the beta distribution is the conjugate prior, meaning the posterior of the parameter mu given observed data, m heads and l tails, and the prior is still a beta distribution, right? So this is beta distribution of mu, like m plus a and l plus b. Right. And we can equivalently say that the prior report in here, A is the prior for the number of heads we believe it will turn out, B being the number of tails. Of course, A and B are not necessarily integers, right? So that's that. I believe we're done. So one word about these workshop notes, as you have seen in this particular session, they're designed to be visual, but not reading materials, meaning they don't have a lot of text in them. You have the book for that. And they're generally focused on the derivations and plots, and I won't try to write the story behind the model down, which again, the book does a pretty good job. There are some of these in last year's slides as well. And I aim to produce no new equations, no new plots. This is another way of saying the book is pretty good. And it's also a way of saying that if you prefer not to listen to the workshop or watch the lecture video, you can survive pretty well with reading the book if you feel you can nail that. Right, and I think I already said the second list of things, and I won't repeat that. So this is basically a recap. We skip one set of details, and I hope it's useful. So I'll pause. We are at time, but if people have some quick questions, I'm happy to take. If not, we will call it a day.
So I have two questions. Can
Yes,
I?
please.
Yeah. The first one is in the 2D Gaussian distribution. You say that if the non-diagonal element entries in the covariance matrix is non-zero, there's a rotation, right?
Yes.
And from this slide, I can guess that the rotation is not exactly a rotation, right? It's like kind of this change in the size of the elliptics, right?
That's a good question. If you remember from your linear algebra class, so sigma is symmetric and real, right? For symmetric and real matrices, they have real eigenvalues, and moreover, sigma is also positive semi-definite, which we won't get to. For these matrices, the rotation matrix, which I just drew on the slide, so these are orthonormal matrices, meaning that these rotation vectors U, they are unit lengths. That's why I have been calling them rotations. So basically for U1 and U2, U1, the norm of U1 is 1, and then the product of U1, inner product of U1 and U2 is 0. So they are perpendicular to each other and they are unit lengths, therefore it only incurs rotation, no stretching.
Okay, so that means the size doesn't change, right?
That's correct. The size don't change.
But from the slides before, I think okay.
Oh, right. So yeah, sorry, that wasn't clear. So for this particular slide, I did not exactly mean that these things, these drawings are exactly the same thing, right? The circle isotopic one is obviously not the same thing as the ellipses. I'm also not. I don't think it's meant to interpret that the second one is exactly the same as the middle one. And furthermore, when I just use the same notation, I don't mean they are the same value. So these sigma 1s and sigma 2s are for each of these plots. They don't translate across.
Okay.
Yeah.
Yeah. And there's another kind of stupid question. I didn't understand. I didn't understand the term unbiased. Can you just give me a quick explanation?
Let me try. Okay.
Yeah.
So let's go there. Right, roughly here. So the okay, I'll make an attempt and maybe I'll post something in writing that is more correct, because this is so basic in stats, and I think there was a question about that it will be hard to mess it up. The notion of unbiased is in the limit of having infinite data, whether the estimator, in this case, sigma ML or a general estimate, sigma tilde or sigma hat, converges to the true underlying parameter sigma squared. Yeah. So this, as I said, expectations are tricky this way. So in this expectation here is in the limit of infinite data. I don't feel like I can be more precise than that, because whether it's multiple data sets or something, but the stats textbook and Wikipedia have a good explanation, I believe.
Thank you. I'll look into it. Yeah.
So thank you for the two questions.
Yeah, thank you so much.
Yeah, in general, thank everyone for good questions. For example, Atika's earlier question was good. Rachel's question was good. Answer was good. So I think this is it for today. Yeah, hopefully next Friday we won't have as much material. as we can see, even for elementary introductory ML, there's a lot more that to cover than we have time for. I'll get a better sense of time. So see you on Monday. Let me stop the recording.